Okay, so we have the question, if a population increases by a certain percent every year, starting with population G, what will be the population after 1 year, 2 years, and 2 years? Then there's another question here that I'll talk a little bit about. Okay, well, first thing you have to understand is that okay, if I'll put some numbers in here. If B equals 9 and equals 24. Just see reasoning. If B is 9, G is 24. Increasing G by B percent means adding 9% of 24. To 24, right? So that's how we increase something by 1%. I think everybody's good with that. So we get 24 plus 0.09 times 24. And again, I think everybody's good. Which is 1.09 times 24. Because you can factor out the 24, it's 24 times 1 plus 0.09, right? So we could write that. This way. We really want to understand that. Because otherwise you're just memorizing a formula instead of necessarily understanding exactly what the formula tells you and why the formula is what it is. And I emphasize understanding it because you remember it better. And it'll be there for you when you need it, in case you just kind of forget the formula. Okay, that can happen. Also, it gives you more insight into what's going on. Okay, well, this is what you have after a year. I'm going to use P of 1, a function P of T for the population, okay? We haven't yet developed what P of T is, but we can say that P of 1 is going to be 1.09 times 24, which is something you need to put into your calculator to get the actual number. After 2 years, we have P of 2, which is 1.09 times P of 1, isn't it? Because P of 1 is what we have after the year. We're going to add another 9%, which means we're going to multiply by 1.09. And that's, of course, 1.09 multiplied by 1.09 times 24, because that's what P of 1 is, right? P of 1 is the 1.09 times 24, multiply that by 1.09. So so now we have 1.09 squared by times 24. Well, so after 1 year, we have 1.09 to the first power times 24. After 2 years, 1.09 squared times 24. Okay, I didn't ask you to calculate it, but after 3 years, well, P of 3 is 1.09 times P of 2, right? In other words, what we have after 3 years is 1.09 times what we have after 2 years. And that equals then 1.09 times 1.09 squared times 24. And that's 1.09 cubed times 24. Okay. Well, now we're seeing a pattern. Every year we multiply by another 1.09. So we have this. Okay. Now, the second question that I posed, this is an extra question because a lot of people got this very quickly. Some using the formula, some reasoned it out, and anything, it looked good. Okay. And I gave you the warning that it looks like you're learning something, so be careful. Now, question is, what equation would you solve to find T when P of T when the population is 50, right? Okay, so give you a hint, the population is 50. P of T is 50 because P of T is your population function, right? And a lot of you wrote that down, okay? At least some of you. Some of you wrote something else down and was, cut out that stuff, and that's okay. Okay? But P of T is 50 and P of T is 1.09. .09 to the T times 24 equals 50, right? Well, that's the equation. Now, you don't know how to solve it yet. Maybe you do because maybe you've seen it in previous courses, or maybe you're in the support course where we've done a little bit with this, and actually you would know how to solve this equation. So I'm going to write down the first step of solving the equation, but I'm not going to write down the rest of it. We don't know the rule yet. We haven't done the inverse function of the exponential, which is what we're going to need to solve it, but that's coming up next week. Okay, so what we get is well, their next step at least is we divide both sides by 24. Which gives us 1.09 to the T equals 50 over 24. which is like about 2.1. We'll keep it 50 over 24. Of course, we could reduce it to 25 over 12. But we're not gonna mess with that anymore. At this point, you need an inverse function to the exponential function. Okay. So now we need the inverse to the 1.09 to the t function. Because if we multiply, or if we take the inverse function of both sides, we're going to end up with t. That's the way inverse functions work. And you should know that about inverse functions. You just don't know what this inverse function is. Okay. Turns out it's a log base 1.09, but that comes later. Okay. Then you're going to find that t is a little over 8. If you raise 1.09 to the 8th, it's almost 2. Well, it's about 2. It's pretty close to 2. And if you raise it to like 8.3, it'll be a little more than 50 over 24. Okay. But again, and those are who are in the, well, actually, that's, just one of you's here today. So I'll put you in the spot. Just shake your head, yes or no. Is that easy to solve? Yeah, that's real easy to solve once you know the rule. Okay. And that's significant. That's it. Some people have 3 tables and 3 graphs already. Some people still working on some of the tables. So let's be clear. 2 to the x, what's 2 to the negative 2? It's 1/4. How do you know it's 1/4? Either because you remember it or because you worked it out, right? Remembering it is not what you want to do. Working it out is what you want to do, because if you know what you did to get 1/4, then you'll know what to do with the 3 to the x and the 1/2 to the x function. Okay. You did the arithmetic, applying the rules to exponents and so forth. So anyhow, you get 2 to the negative 2 equals 1 over 2 squared equals 1/4. Whenever you write out this table, I really prefer to see that you write out these steps to reinforce what the negative exponent means, because people tend to lose track of that. One of the reasons we do this first thing in the semester. Another is, well, it's really important. And in many ways, 2 to the negative 1. 1 over 2 to the 1 is 1/2. 2 to the 0 is 1. 2 to the 1 equals 2. 2 squared equals 4. Then we can put points on the graph. Here's 1, point is 1, here's 1/2, and down here's 1/4. So let's say 1/2, that's what we're going to get when x is negative 1, and 1/4 is what we're going to get when x equals negative 2. And when x equals 1, we're going to get 2. When x equals 2, we're going to get 4. We're going to have a graph that looks like this. Now we're used to 4 being a little higher, so the graph looks a little steeper, a little curvier. That's just relative to the scale we use. Okay. And to get the 3 to the x function, we're going to need to use scale up here. Okay. So imitating what we did for the 2 to the x, write out your table for 3 to the x. If you didn't already, write it out with the arithmetic. Now, if you got everything and you got the graph and everything, then I know you know how to do it, so don't worry about it. But if you haven't written this one out here, write it out again. And write it out with all the arithmetic. And some people still have a little difficulty with that, although it's doing pretty well. Okay, so if x is -2, 3 to the x is 3 to the -2. Now, if you've written that much down, then you're doing just fine. Okay, but then what's 3 to the -2? It's by the rule. Again, a to the -b is 1 over a to the b. For any number a and any number b. So 3 to the -2 is 1 over 3 squared, which is 1/9. So let's have a little more room here. Okay. And 3 to the -1. 1 over 3 to the 1, which is 1/3. 3 to 0 equals 1. 3 to the 1 equals 3. And 3 to the second is 9. Okay. So now we can graph 3 to the x. Now let's go ahead and use a little color. Now 1/9 is like 1/9 of this. So we cut the interval from 0 to 1 into thirds and then cut those intervals into thirds and we get 1/9, but it's going to be down here more than twice as close to the x-axis as 1/4. Understand the numbers, you see that. So it's going to be down here about like this, which means that your point is going to be closer to the x-axis than this one, and this one's pretty close. So I'm going to just smudge that in there. And then 1/3 is going to be somewhat less than 1/2. But then, of course, when x equals 0, you're going to get 1, just like you did for 2 to the 0. So the graphs are going to pass through the point 0, 1. Then you're going to get the point 1, 3 and the point 2, 9. So the graph of 3 to the x starts lower than the graph of 2 to the x, crosses the graph of 2 to the x at the point 0, 1, and then starts taking off. Now, what about 1/2 to the x? Okay. One-half to the -2 means what? It means 1 over 1/2 squared. That's your rule. A to the -b is 1 over a to the b. It applies here just like it does everywhere else. It doesn't change. The numbers change, but the rule doesn't. And that's 1 over 1/4. Which is 1 times 4 over 1, which is 4. Now you really have to understand that arithmetic in context. You have to understand that dividing by a number is multiplying by the reciprocal, or dividing by a fraction is multiplying by a reciprocal, and understand that a to the -b is 1 over a to the b for any number a and any exponent b. Okay? Those two rules go together to give you this. Okay, then. One-half to the -1 is 1 over 1/2 to the 1. Which is 1 over 1/2. Which is 1 times 2 over 1. Which is 2. And really, all 1 divided by 1/4 is saying is, how many 1/4 do you need to make 1? How many quarters do you need to make $1? Okay? So you got 1/4, another 1/4 gives you 1/2, another 1/4 gives you 3/4, another 1/4 gives you 4/4, which is 1. So you can count to 1 by 1/4, and you need 4 of them. That's all this calculation tells you. If you divide 1 by 1/2, it asks how many 1/2s does it take to make 1? So it takes 2 halves to make that. So the answer is 2. And the formal calculation is just what you do when you don't want to have to think that hard, or when the fraction's kind of nasty. Like what's 1/411? Well, it's 11/4, but that's a little less than 2. But the rule is the same. Okay, well then, 1/2 to the 0 is 1. Is any number to the 0 is 1. 1/2 to the 1 is 1/2. 1/2 squared. Now this one is a fraction, so we better go ahead and write it out. That means 1/2 times 1/2. And you multiply the numerators, you get 1, you multiply the denominators, you get 4. So now we've got 5 points. We can construct a graph. And there's a gremlin that must be eating my pretty colored chalk. But okay, so I'll put a purple circle around this to indicate that that's going to correspond to the purple graph. And at -2, I'm going to get 4. So at -2, I'm going to get 4. So I've got this. So here's a point. At -1, I get 2. So at -1, I get 2. Well, that's going to be a point right about here. At x equals 0, I get 1. Same doggone thing, same point. Okay. All these functions gang up on the point 0, 1. And then the point 1, 1/2. No, it's here. The 2, 1/4 is here. And now we get this graph, which is just a mirror image of the 2 to the x, right? So we can label these. Just want to keep track. Here's y equals 2 to the x. Here's y equals 3 to the x. And here is y equals 1/2 to the x. Now, if you can construct these graphs, it tells you a lot about how the graphs of exponential functions behave. And there's another really important exponential function that I'm going to mention right now, because we're going to see it. It's all over the place. It's really, in the context of calculus, the simplest of your exponential functions. 2 to the x seems pretty simple, right? And for this course, it is. E to the x is even more simpler. Okay? It's the simplest possible exponential function for reasons that you'll be able to understand in calculus, but I'll kind of mention right now. Okay. Now, this is really your most important exponential function. It's a function that makes the universe go round. Okay. That's maybe an exaggeration. E. Wish we get the chalk here. I mean, college didn't do it, but I'm ordering online. I can't find your chalk. Okay, E is approximately equal to 2.7. Now, a little more exact, it's 2.718. Okay. 2.7128. Boy, losing it. 2.7128, 2.7128, 7128. And it seems like it's going to repeat that 7128, but it doesn't. Now that 7128 will come up somewhere later, about every 10,000th. Group of 4 will be at 71828 every 10,000. But it's an irrational number. It never ends, and it can't be approximated by fractions. I mean, it can be approximated by fractions, but not a fraction. It's not some integer divided by an integer. Okay. Never-ending decimal expansion. The calculator will give you about 10 places probably, which is enough for most applications, but not all. Okay, so my point is, E is approximately 2.7. So where should the graph of e to the x go? Where do you think the graph of e to the x will be in this scheme here? We can discuss this a little. Okay, to understand the graph of e to the x, at least where it goes in this scheme, think about what you'd do if you made a table. Well, we saw that if you plug in x equals 2 in a graph of e to the x, you're going to be squaring 2.7, right? Just like if you do the 2 to the x graph, if you plug in x equals 2, you get 2 squared, right? If you plug in 2 to the 3 to the x function, you get 3 squared. Well, if you plug in 2.7, you're going to get 2.7 squared. And 2.7 squared, well, 2.7 is bigger than 2, so 2.7 squared is going to be bigger than 2 squared, right? It's going to be bigger than 4, in other words. It's going to be less than 3 squared. So you know that your point on the e to the x graph corresponding to x equals 2 is going to be between here and here. Because 2.7 is between 2 and 3. Okay? So we can just make a guess. Now 2.7 is a little closer to 3, it's quite a bit closer to 3 than it is to 2, right? So 2.7 squared is probably going to be closer to 3 than it is to 2. So we can just make a guess, okay? Let's put a point here, and we can put kind of a question mark, because we're not sure how close it ought to be to 2, 3, but we're pretty sure it's going to be closer to 3. Now, of course, when x equals 1, we're going to get just e, which is about 2.7. So, well, here's 2, and here's 3. So where's 2.7? Well, 2.7 would be about here, right? So we know what that point is. We also know 2.7 to the 0 is 0, so it's going to go here. (2.7) to the -1 is going to be between 2 to the -1 and 3 to the -1. 2 to the -1 is here, 3 to the -1 is a little lower. So the graph is going to be sandwiched in between these, and it's going to be sandwiched in between these. So we're going to have this graph that I'm not going to draw too dark. It's sandwiched in between the 2 to the x and 3 to the x graph here. And then it goes like this, okay? So this is y equals 2.7 to the x, which is approximately e to the x. I swear it's a chalk and not me, but you believe that or not, doesn't matter. Okay, sorry, that E has to come out a little bit better than that. See a lot of pressure, go slowly. I can make the chalk go where I want it to go. Okay, so that's your graph. Approximate graph of e to the x. It's around here somewhere. Between 2 to the x and 3 to the x. You can easily do 2 to the x and 3 to the x. And then it's easy to draw a curve that's got the same basic shape, but a little closer to the 3 to the x than the 2 to the x. Okay? That's a very important function, maybe the most important function in mathematics. Okay? Very good candidate for the most important function. It has the property that the slope of the graph at any point is equal to the value of the graph. So the slope of the e to the x graph at this point should be 1. At this point, it should be e, which is about 2.7. At this point, it should be 2.7 squared. The slope should be equal to the value, okay? So the further you are from the x-axis, the steeper the graph. And it's an exact correlation. Okay, that's a little preview, but you might want to carry that with you into your calculus class. And you'll see more about it there. Oh, man, there's garbage on the screen. Okay, now, we can kind of generalize what we see here. Like, let's do one more graph. What would the graph of y equals 1 to the x? Well, show me with your fingers, one hand or the other, use two hands if you need them. If we're doing y equals 1 to the x, what would you get when x equals -2? Well, 1 to the -2 is 1 over 1 to the 2, right? What's 1 squared? 1. What's 1 over 1? Be sure you hold up the right finger. Okay, now, okay, makes sense? Okay, what about 1 to the -1? What are you going to get? Yeah. Okay, you get 1. Okay. 1 to the 0. Well, any number of zeros, 1, so you know that's going to be 1. What's 1 squared? Sorry, what's 1 to the first power? It's 1. What's 1 to the second power? It's 1. What's the y value for this function? Always going to be, no matter what x is. It's going to be 1. So we draw the graph plus 1. So it's terrible. Trying to make a line that clearly contrasts with the rest of them. Okay. This is y equals 1 to the x. Now, how does the graph change if you go from 3 to the x to 2 to the x to 1 to the x? How would you describe the change? It kind of flattens out, right? What happens if you go to 1/2 to the x? Well, it unflattens itself, but in the opposite direction, right? Okay. So we can say that well, we can say several things. Let's start saying. So we can see that first of all, if b is greater than 1, the graph is concave up, isn't it? Because it doesn't get flat until b equals 1. Okay. And let's say if b equals 1. If b equals 1, the graph is flat, it's horizontal, its slope is 0. It's the most boring graph you can imagine. Okay? I don't want to say if b equals, I want to say if b is greater than 1, which is what I started to say a minute ago. Okay, if b is greater than 1. What can you say about the graph? Well, the graph is concave up, isn't it? It's rising steeper and steeper. It rises more and more steeply. Concave up. More overall curvature for greater B. And I'm saying that, but it's not really true because over here it's got less curvature. Okay, more curvature on the right and less curvature on the left. So more curvature on the right for greater B. I'm not going to complete the statement about less curvature on the left, but you know what's going to happen is if B is a big number, it's going to come down here very quickly. It's going to go through here and then it's going to dive down to where it's almost on the x-axis. Then it's going to be almost flat. Okay. So those are characteristics that you want to understand. And if B is less than 1, it's still concave up. Okay. Just like this one is, but it's decreasing. Okay. That's another thing. Y equals 1/2 to the x is a reflection of y equals 2 to the x through the y-axis. Okay, you can see the reflection. We pointed it out before, but just to be sure. Okay, here's your 1/2 to the x. Here's your 2 to the x. If you reflect this point through the y-axis, you get this point. Reflect this point through the y-axis, you get this point, and so forth. Okay. And that comes about because of this rule for negative exponents. And the rule for fractions, dividing by a fraction. Okay, so these rules go together to make this happen. So general y equals 1 over b to the x. Is a reflection of y equals b to the x through the y-axis. We got a function like Y equals 40 times 1.5 to the x. First of all, where's your 1.5 to the x graph? Well, 1.5 is between 2 and 1. This is 2 to the x. This is 1 to the x. So it's going to be in between here. Okay. But it's also going to be vertically stretched by factor 40. Well, I'm not even going to try to draw a graph stretched by factor 40. That's too big of a stretch. But it's going to be a graph between here and here. Except that instead of like having 1 here, this would be 40. Instead of having 2 here, it would be 80, and so forth. Okay. Well, you understand vertical stretch, I hope. And vertical shift, yeah. Okay. Now we can do a horizontal shift, but we usually don't need to in an exponential function. But horizontal compression is kind of a big deal. Okay, so your text talked about horizontal compression. We haven't talked about it much in class. Because if you get down to vertical shift, horizontal shift, and vertical stretch, it's a little easier to understand horizontal compression. Okay. So let's say you got y equals 1.5 to the 3x. Okay. Well, your graph of 1.5 to the x isn't hard to sketch if this is 1 here, and then up here's 2. Y equals 1.5 to the x is going to be, we're going to have a point 2, 2 and a fourth. It's going to have a point 1, 1.5 or 1.5, and have a point 1, 0. It's going to have a point down here that's, well, it's actually going to be 2/3, and then it's going to be 4/9. And it's going to look like this. And here's y equals 1.5 to the x. Now, to get 1.5 to the 3x, what do we have to do? Well, if x equals 1, 1.5 to the 3x would be 1.5 to the third, right? And 1.5 to the third is 3 3/8. Okay. It's about 3.375. But, up here's 3. And up here is the point 1.5 to the 3 times 1. So it's a lot higher. You're taking a bigger power because you're multiplying by 3. Of course, the graph still goes through this point. Then we have a point here. It's way down here. This is -1. 3.5 times, but 1.5 to the 3 times -1. Okay, which is 1.5 to the -3. which is a little less than a third. So it's a lot lower. So your graph is going to look like this. It's going to go up real steeply here. Shouldn't hit the x-axis. Gets real close to the x-axis pretty quickly. Okay. Well, that's what we get if we squish the graph of 1.5 to the x 3 times closer to the y-axis. Okay, so every point, let's just take a line here. So it looks like this point is 3 times closer to the y-axis than this one. Is that reasonable? Well, let's see, here's 1, 2, 3 of these. Yeah, it looks like it matches up pretty well. Okay. So every point of y equals 1.5 to the 3x is and y equals 1.5 to the x. Okay. Now that's an important property. So if you multiply your y value of 1.5 to the x by 40, it gives you vertical stretch. But if you multiply the x by 3, it squishes things in by a factor of 3. Squishes things in toward the y-axis. Okay. Now you put these properties together and you get more information about the graphs of various exponential functions, including the one I showed you on that screen. Okay, you had an upside down exponential function there. Well, if you just multiply any one of these by -1, all your y values go negative, and the graph just gets reflected through the x-axis. As you should know from chapter 1, but yeah, we're still sorting out transformations. Okay. So turns the graphs upside down and reflects it through the x-axis. So if I take, let's say, this graph and turn it upside down, then it looks like this. Then I can raise it up and it ends up being the graph that you saw. Do you remember what that looked like? Okay. You can look at it through a lot of people. Turns upside down and gets raised up. And that's an important thing that happens to graphs. Now, you're going to have to work through the details of this, but those are the fundamental ideas behind the graphs of exponential functions and how you transform them. Now, you've done quite a bit with transformations, so that part ought to be accessible to you. Okay. The only additional transformation we haven't talked a lot about, again, is the compression. So that's what we just did. Okay, good luck.